section 4.4. We've talked a little bit about these items, but um, the design of combinational circuits starts from the specification of the design objective and culminates in a logic circuit diagram or set of Boolean functions from which logic diagram can be obtained. And this procedure involves the following steps. From specifications of the circuit, determine the required number of inputs and outputs and assign a symbol to each. Derive the truth table that defines the required relationship between inputs and outputs. Obtain the simplified Boolean functions for each output as a function of the input variables, and then draw a logic diagram, verify the correctness of the design, manually or by simulation. I got an example down here. And first off, code conversion example. Available large variety of codes for the same discrete elements of information results in use of different codes by different digital systems. It is sometimes necessary to use output of one system as the input to another. A conversion circuit must be inserted between two systems if each uses different codes for the same information. Thus, a code converter is a circuit that makes the two systems compatible even though each uses a different binary code. To convert from binary code A to binary code B, the input lines must apply the bit combination of elements as they are specified by code A, and the output lines must generate the corresponding bit combination of code B. Let's see. Here's an example. First off, we got a truth table for the code conversion. So here's our BCD, and again, this is a way you can represent data. And we got our ABCD values here. And if you want to convert that to the output XS3 code, then this would be the conversion that would take place. Now it says the maps in figure 4.3 are plotted to obtain simplified Boolean functions for the outputs. Each one of the four maps represents one of the four outputs of the circuit as a function of the four inputs. The ones marked inside the squares are obtained from the minterms, make output equal to 1. The ones are obtained from the truth table by going over the output columns one at a time. For example, a column under output Z has 5 ones. Therefore, the map for Z has 5 ones, each being in a square corresponding to a minterm that makes the Z square equal to 1. Okay. That's what they're pointing out down here. For like your W, that has your 5 ones there. Down here, your W has the 5 ones here. And that corresponds to this, this setup here. Now, some of these I could see, and I could derive it. You know, like, let's see. They indicate Z is equal to D prime or not D. And you look at it, Z1010, D0101. You know, as I keep going down, 1010, 0101, 1001. You can see that they're complements of each other. So pretty easy to tell. Some of these other ones took me a long time to come up with this this equation down here, like y is equal to CD plus C prime D prime. But anyway, they got these. They come up with are ones. Remember the X's is those don't matter. Those we don't care. And for the table here, like this one right here, if you start out with the table itself, actually, let me show it. Better. So A, B, C, D. I got 4 by 4. It's 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0. Okay. Luckily, we do not have to look at them to see that. I could no more see that one than fly to the moon. But if I'm trying to look at, which one did I say I was going to look at? I guess it doesn't matter. But if I want to look at X, for example, down here for X, I guess this one right here. If I were to come across, this would be 0, 0, 0, 1. And let's see, so it's not A, not B, A prime, B prime. This would be A prime or C prime and D. This one right here would be our let's see, A prime, B prime, and then C and D. And so when you're looking at these correspond directly to your A, B, C, and D here. And our X being 1 here, you see is 0, 0, 0, 1. 0, 0, 0, 1. And we have 1 there. So if I come up here, this one 0, 0, 0, 1. So 0, 0, 0, 1. There's a 1 there. See, this one is 0, 0, 1, 0. 0, 0, 1, 0 is a 1 there. And this one is 0, 0, 1, 1. 0, 0, 1, 1. Am I putting all those in the right place? Let's see. 0, 0, 0, 0, 0, 0. Yeah, I am. Okay. This one is 0, 1, 0, 0. 0, 1, 0, 0. This one would be 1, 1, 0, 0, 1. 1, 0, 0, 1. Assuming I put them all in the right place. Then you see I come up with these right here. Okay, now how do they determine that I don't care? Each one of the four maps represents four output circuit. Okay, the ones marked inside are obtained from the minterms make output equal to 1. The ones are obtained from the truth table. Going over the output. Okay. For example, output under column Z has 5 ones there for the map for S being 1s. Good, I just mentioned that. 6 don't care minterm 10 to 15 are marked with an X. I see. Reason why is because this does not have all the values associated with it. Like my next one, if I were to build this table, would be 1 0 1 0 1 0 1 0. Let's see if that's right. Yeah, X there. So the other ones, let's see if I can eyeball them. What did I say? 1 0 1 0. My next one would be 1 1 0 0. Not in any kind of order. 1 1 0 0. Okay. 1 1 0 0. Actually, I can just use these up here. 0 0 0 0 0 0 0 0 1 0 0 1. So the remaining ones, starting with here, would be the same except for they have a 1 there. So 1 0 1 0 1 0 1 0 got an X. Okay. 1 0 1 1 1 0 1 1 1 0 1 1 X. 1 1 0 0 1 0 0. Okay, I got that. 1 1 0 1 1 1 0 1 1 1 0 1 1 3 ones and a 0. And last one, all ones. 1 1. So assuming my eyes didn't get off, that should be where they came up with the yeah, that right there. Okay. Now the idea is we're trying to do groups, pairings on this to simplify it. And remember, we'd like them, we'll have to be in groups of like 2, 4, so forth, 8. I guess I do got next there. They pair these two together with these two because that creates a group 4. And remember, if they're different, then you ignore that. So these 4 right here, and it looks like they pair these 2 together. Because again, you don't want it by itself. You can pair it with something else. Pair with something else, and something disappears. So they're pairing these 2 together, and they're pairing either those 2 or this one and this one. Let's see what they do. All those 4. Because again, if you pair 4 of them together, you get 2 atoms disappear. Okay, so they're pairing these 2 with these 2, like that. Now this one over here, If I come over here, this is A is 0, B is 1. This is A is 1, and B is 1. The 0, remember, is primes. 1 is just the normal variable. Now here's our B, C prime, D, our very last term here. This corresponds to this right here. Since A is different, it drops away, but B is 1, B is 1. That's why we have B. If I come straight up to the top here, this column, C is 0, D is 0, that's C prime and D prime. So that's where they get this last one, B, C prime, D prime. Okay, now the red right here. If I come straight over to the far here, this is A is 0, B is 0. This is A is 1, B is 0. A is 0, B is, or A is 0, A is 1. That's different, so it drops away. B is 0 remains. So that's my B prime. If I come straight up, red-wise, again, the first one here is C, this is D. So C is 0, D is 1. C is 1, D is 1. The C's are different, so they drop. D is 1, D is 1, so that's D. So that's where they get this one, B prime D. Plus, now we're looking at the purple. Coming over to the left here, A is 0, B is 0. Coming over to the left here, A is 1, B is 0. A's are different, so we drop the A. B is 0, so we keep our B prime. Coming straight up, this would be C is 1, D is 1, C is 1, D is 0. The D's are different, so I drop them, and I keep C is 1, which is C, which was where they get this at. Now, what this gives us a simplified version of that expression. And specifically, they're doing that for, I won't do it here, but they're doing it for all 4 of these. So that's how you would derive this just from the truth table. Like I say, I could no more look at that and come up with that and fly to the moon. But if you do the simplification here and map the 1's and I guess the x's, then that helps. Does that make sense where everything came from on that? Yeah. Okay. Uh-huh. You try to have the biggest group you can. And the reason why is if you group 4 of them together, then 2 of your variables will disappear. Yeah, because originally, remember I said I thought maybe we could group these 2 together? And if you did that, well, if I went over here, I'd have A is 0, B is 0, so that would keep me A prime, B prime. And going up, I'd have C is 1, C is 1, and D is 1, and D is 0. The D's are different, so that keeps C. And so, yeah, it won't be as simplified. Yeah. Okay. So then they list all these down here. Um, hmm. Let's see. Two-level logic diagram obtained directly from the Boolean expression is derived from the maps. Various other possibilities for logic diagram that influence the circuit. Okay, they're showing expressions obtained in figure 4.3 may be manipulated algebraically for the purpose using common gates for 2 or more outputs. Okay, I was wondering what they're doing. You see here they have C and D, but here they have C prime and D prime. So by using some simplification, they can put everything in terms of C's and D's, and they have less inverters for whatever reason that would be beneficial. Here they started out with 3 inverts, and B, C, D, and so 6. So 6 inputs, and by doing a little bit of simplification, they took it down to 4. They still had to have B prime and B, but they took it down to 4 instead. So gets rid of an inverter. This is just a logic diagram demonstrating it. Z is coming from here, and that's equal to D prime. So D's coming in here, going through an inverter. Y is CD plus C plus D inverted. Okay. Here's my first part, the CD, C and D. So it's coming in. And C and D are branching down here into a OR gate. And that's what the C plus D inside of the parentheses is right here. And then this plus in between them is this OR, get that away, is this OR gate right here. So it's taking the invert of that. That's because that has a prime after the C plus D. X B prime. Okay, there's the inverter coming in there. So there's B prime, C plus D. C plus D is, okay, coming down from there. And then plus, it's coming in through this inverter here, B, which is coming into there, C plus D prime, which is coming down from there. Going to that. W, A plus A plus is our OR gate. B times C plus D, C plus D, or C, okay, C plus D is coming in there. And then B times, or and C plus D, and coming in there. So that's a logic diagram. Probably wouldn't have noticed that myself. But then again, I'm not going to design electronic devices. They reused. See here, C plus D. And down here is C plus D. No, go away. And it had C plus D here. And so by rewriting those, besides using less inverters, they also used C plus D in 3 places, which is why the C plus D right here is branching down and being used in 3 places. Like I say, I don't think I would have noticed that kind of simplification. But, okay. Not counting input converters, implementation in some products form requires 7 AND gates and 3 OR gates. Implementation of 4.4 requires 4 AND gates, 4 OR gates, and 1 inverter. If only normal inputs are available, the first implementation will require inverters for variables B, C, and D, and the second implementation will require inverters just for variables B and D. Thus, the 3-level logic circuit requires fewer gates, all of which in turn require no more than 2 inputs. And general multi-level logic circuits exploit subcircuits can be used to form more than one output. Hence, C plus D is used in forming X, Y, and W. The result is a circuit with fewer gates. Logic synthesis tools automatically find and exploit subcircuits that are used by multiple outputs. So this looks like even if you're in design, going to electrical engineering, perhaps, or computer engineering, they got tools that'll do that for you. Now, section 4.5 is talking about the binary adder subtractor. Digital computers can perform a variety of information processing tasks. Among the functions encountered are the various arithmetic operations. Most basic arithmetic operation is addition of two binary digits. This simple addition consists of four possible elementary operations. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 2, which in binary is 1, 0. Now this is not the same. They're not talking about the OR gate that we referred to. So they're actually talking about addition in terms of binary and subtraction. Let's see. They're talking about it being a carry. We got a something called an adder that'll help us with this. Says a binary adder subtractor is a combinational circuit that performs arithmetic operations, addition, subtraction with binary numbers. We would develop the circuit by means of a hierarchical design. Half adders carried out first, from which we develop a full adder. Connecting in full adders and cascade produces a binary adder for two n-bit numbers. Subtraction circuit is included in complementing circuit. First off, just the principle behind it. 0 plus 0 is 0 with a carry of 0. 0 plus 1 is 1 with a carry of 0. 1 plus 0 is 1 with carry of 0. 1 plus 1 is 0 with carry of 1. Now here, it talks about simplified Boolean functions for the two outputs can be obtained directly from the truth table. The simplified sum of products form are given by this. Okay, I could see. If they hadn't given that to me, I would have saw C, because 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, 1 times 1 is 1, so that's the and. C is equal to X and Y. This should be a lowercase y, but okay. What I saw S, let's see. I don't think I would have saw S. But they give it to us. S is equal to X prime Y plus X Y prime. I probably would have figured it out. Because X is 0, 0, 1, 1, and Y is 0, 1, 0, 1. And the logical thing to do is at least have a column for X prime and Y prime. And so then this would be 1, 1, 0, 0. This would be 1, 0, 1, 0. And I suppose you could try lots of different combinations so you'd see which one matches, X, Y, X plus Y, so forth, to visualize it. S 0, 1, 0. Now, sharp people would be able to not build all these columns in here to see that, but I would have probably had to go through and do it, try all the different combinations, and then see which one it matches. So, But anyway, don't have to do that because I've already got that for us in this. Does that make sense how you would come up with that though? Okay. And it's like, I don't know how many columns that'd be. Probably 4, 8 of these columns along with what I already have on here. So, and then even then, I may not see it. I may have had to even add all those or so forth. And Excel wouldn't be too bad. Okay. Now, once we come up with that, these forms, then to implement them in a circuit. And again, when we talk about a circuit, realize that we're talking about voltage coming through here. So they're using voltage to add these two numbers together. So as weird as that seems. So C down here are carry. We have X and Y coming into an AND. S, we have X prime Y coming in. And then X, Y prime coming in there. And then there's a plus in between them. So that's where that's coming from. It could also be input with an exclusive OR and an AND gate. This. This form is used in the next section to show that two half adders can be used to construct a full adder. Okay, so a full adder. Addition of n-bit binary numbers requires the use of a full adder. The process of addition proceeds on a bit-by-bit basis, right to left, beginning with the least significant bit. After the least significant bit, addition in each position not only adds respective bits, but also must take into the carry into account. Like here, we got, they give an example of three inputs here. Okay, let's just talk about it. 0 plus 0 plus 0 is 0 with carry of 0. 0 plus 0 plus 1 is 1 with carry of 0. 0 plus 1 plus 0 is 1 with carry of 0. 0 plus 1 is our 2, which in binary is 0 with a carry of 1. 1 plus 0 is 1 with a carry of 0. 1 plus 0 plus 1 is 2. In binary is 0 with a carry of 1. 1 plus 0 is 2, same thing. 1 plus 1 is 3, which is in binary a 1 with a carry of 1. So that just shows them. You see the X, Y, and Z we got here. So what they do is they can map these. So the X, Y, Z, and see what C and S gives you. Like S here is a 1, which is 0, 0, 1. And S, which one's S? 0, 0, 1. That's why they put a 1 here. Another one that has a 1 is this one, which is 0, 1, 0. 0, 1, 0 is right here, so they put a 1 here. Now I notice I don't have any X's, and then they continue. I notice there's no don't care, and that must be because there's 8 boxes down here, and there must be 8 lines here. 1, 2, 3, 4, 5, 6, 7, 8. And so there's no don't care. The don't care comes when there's like 10 boxes down below and there's only 8 lines here. Okay. So they've mapped all this. None of these are next to each other. So you notice that all four of these, they have to write all three letters. Like this one, this x coming over here, that's x equals 1, so that's x. This is y is equal to 0, z is equal to 0. So for the box M4, that'd be x, y prime, z prime. X, y prime, z prime, which is our third term here. This one would be x prime, y prime, z, x prime, y prime, z, which would be this first term. This one would be x, y, z, which is our last term. And this one would be x prime, y, z prime. X prime, y, z prime, which would be our second term. Now over here, when I do the mappings of the ones for our carry, again, that's 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. When they do those mappings, then they have some overlap. And so they want even if they can. So they group these two together, group M5 and M7 together. Those kind of hard to see. And group M3 and M7 together. The grouping of M5 and M7 gives us X. Let's see. Y's are different, Z's are the same, so it gives us XZ, which is this one. The grouping of M3 and M7 together. Come over here, the X's are different, so drop those. Coming straight up, both of those, that gives us Y1, Z1, so YZ, which is our last term. And then a grouping of M7 and M6. If I came straight over, that's X. Coming straight up, I got Y is 1, Y is 1, Z is 1, Z is 0. Z's are different, so I drop them. So that gives me XY, which is our first term. Logic diagram for full adder implemented in sum of products is shown in figure 4.7. It can also be implemented with 2 half adders and 1 OR gate, as shown in figure 4.8. And sure enough, it looks like it adds it. So they're showing how if you started down here and you went backwards, you could come up with this exclusive OR arrangement. There's our S. There's our C, and that's based upon these right up here. So they're showing it here, but they're implementing it with the circuits here with our 4 AND gates and the OR gate. Now that looks weird because that's the line that goes beyond, but that's still just an OR gate. And then 3 ANDs here and an OR gate for the carry. Okay, so to implement it with the this form right up here. So our exclusive OR gates, XOR. X and Y are coming into our XOR gate. It gives us X XOR Y. That comes in input here, which comes in from Z. And that's because the S is equal to that right there. Now, in addition, our carry They don't specify it up above, but our carry, I wonder why they don't show that. Our carry, if we put it in terms of our XOR, is given by this over here to the far right. So we have X and Y right here coming into an AND gate. And they're coming in here to the OR, which is coming from that. And then this comes from this AND, which comes from Z, which is right here. And then our X XOR Y, which is coming from right there. Okay, so they're showing how you can do the full adder in the sum of products form. Okay. Now binary adder. The idea here is that you could have many digits. Not just two, not just three. Binary adder is a digital circuit that produces a arithmetic sum of two binary numbers. It can be structured with full adders connected in cascade, with the output carry from each full adder connected to the input adder, the next full adder in the chain. And it's really interesting when you get down to the design of this. But addition of in-bit numbers requires a chain of in full adders or a chain of 1/2 adder and n-1 full adders. In the former case, input carry to the least significant position is fixed at 0. Figure 4.9 shows the connection of 4 full adders to provide 4-bit binary ripple carry adder. Now, when we're talking about A0, A1, A2, and A3, we're talking about like this number here. 1011. The far right would be our first position, as 0th position, subscript 0, then 1, then 2, and then 3. You notice down here they refer to A as the augend. If I'm saying that right, it's been so long. 1011. They're referring to B. B is 0011 as the addend. I'm saying that right. And they got the labels right there. Now, if we just think of it, starting right here, A plus B. 1 plus 1 is 0. Oops, 0 right here. And we carry the 1. So it's putting a 0 here in the index of 0 position, so S sub 0. But then in the carry, which is C sub 1, it puts a 1. So it puts it in the next one. Then add these together. Your previous carry plus A and B, 1 plus 1 plus 1 is 1, with a carry of 1. So it's going to the next position. Then 0 plus 0 plus 1 is 1, with a carry of 0. And at this point, adding these together, 0 plus 1 plus 0 is 1. And you see there's no carry for the next piece there. Plus, the carry, there is no carry for the first one here. So that's a thing to note. General idea behind it is you take each one of the digits, like A0 and B0, which would be this digit, and this digit, and add those together. And not sure why they have C0 coming in there, because I don't really use C0. But anyway, you have your sum, and then you carry, and a carry goes over the next full adder. That takes that values of A and B, and then that C, adds it together, and then does a carryover for that. Okay. This is an interesting idea. The carry propagation. Addition of two binary numbers in parallel implies that all bits of the augend and addend are available for computation at the same time. As in a combinational circuit, the signal must propagate through the gates before the correct output sum is available in the output terminals. Total propagation time is equal to propagation delay of a typical gate times the number of gate levels in a circuit. The longest propagation delay time in an adder is the time it takes to carry to propagate through the full adders. Just keep in mind, what we're talking about here is voltage coming through. So it's assuming that these are coming in at appropriate time intervals. If A1 is arriving here and B1 has yet to arrive, then that would mess up the mechanism. Where does it talk about it? Oh, there it is. Number of gate levels for the carry propagation can be found from the circuit of the full adder. The circuit is redrawn with different labels for convenience. The input and output variables use subscript I to denote a typical stage of the adder. The signals at P sub I and G sub I settle to their steady state values after they propagate through the respective gates. These two signals are common to all half adders and depends on only the input augend and addend bits. Signal from the input carry C sub I to the output carry C sub I plus 1 propagates through the AND gate and OR gate, which constitutes two gate levels. Okay. Carry propagation time is an important characteristic of the adder because it limits the speed with which two numbers are added. Though the adder, or for that matter, any combinational circuit, will always have some value at its output terminals. The outputs will not be correct unless the signal is given enough time to propagate through the gates connected from the inputs to the outputs. So it doesn't matter if the voltage is not there when it's supposed to be. It goes ahead and calculates it anyway. So it's not like you're writing some kind of complex program on that. It's relying that the design is done correctly. Otherwise, you get, like they say, incorrect results. Several techniques for reducing the carry propagation time in parallel adder. The most commonly used technique employs the principle of carry look-ahead logic. Okay, got the full circuit of the full adder. We find two new binary variables, P and G, in this manner. The output sum and carry can be expressed as this right here. G sub I is called a carry generate, and it produces a carry of 1 when both A and B, A sub I and B sub I are 1, regardless of the input carry, C sub I. G sub I indicates that data into stage I generates a carry in stage I plus 1. And P sub I is called a carry propagate because a term with a carry into stage I will propagate into stage I plus 1, so forth. So they're rewriting these, our input carries with the propagation built in. And then this right here, C sub 3 is equal to all this. And then there's our carry. C0, of course, this is brought in. Even though this has a default value, then it affects that. Construction of a 4-bit adder with a carry look-ahead scheme is shown in the figure 4.12. Each sum output requires two exclusive OR gates. The output of the first exclusive OR gate generates a P sub I variable, and the AND gate generates the G sub I variable. The carriers are propagated through the carry look-ahead generator, and applied as inputs to the second exclusive OR gate. All output carriers are generated after delay through only 2 levels of gates. Thus, outputs S1 and S3 have equal propagation delay times. 2-level circuit for the output carrier C4 is not shown, and this circuit can easily be derived by the equation substitution method. Binary subtractor. Subtraction of unsigned binary numbers can be done most conveniently by means of complements. We looked at that before. Remember, the subtraction A minus B can be done by taking the 2's complement B and adding it to A. So we rewrite our subtraction as addition using the 2's complement. 2's complement can be obtained by taking the 1's complement and adding 1 to the least significant pair of bits. So it looks like they're taking the they're working with the 2's complement of B, I guess. Or specifically then working with the 1's complement. But that's why B is being sent into this XOR gate. I'd have to look at the XOR table to see what this M is doing when it sends that in, but that refers to it. Overflow. 2 numbers with n digits, each are added, and sum is a number occupying n plus 1 digits. We say that an overflow occurred. Like this, I was trying to find an example. This up here shows that there's a carry coming off here, but it doesn't necessarily have a place where it can go. So that's what they're referring to. Okay. There it is. An overflow condition can be detected by observing the carry in the signed bit position and the carry out of the signed bit position. If these 2 carries are not equal, an overflow has occurred. Because if our first one is a 0, because we don't have a carry to begin with, and then our last one is 0, they're the same. But the last one is carrying over a binary digit of 1. That means that overflow has occurred. That's what they're saying. The 2 carries are applied to an exclusive OR gate. An overflow is detected when the output of the gate is equal to 1. Because if I remember right, The XOR gives you a 1 if exactly one of them is a 1. So if they're different, then it gives you a 1, which is why the XOR gives you your overflow condition. Now, I wasn't sure when I saw this up here. They say with overflow detection, because I don't see C sub 0 being sent through an XOR with C4. If you send C0 and C4 through the if you send C0 and C4 through an XOR gate, then that would tell you the results of whether you have an overflow or not. This just simply sends it on to C. I guess don't even show it really. Well, that's a good stopping place because we're 4 minutes away, and I can't really get into 4.6 very much on that. So we'll stop there. If I go out, the test 3 is out there for the previous chapter. You can do that to scan work. You can use CAM scanner to bring it in. If you want to type them in, you can, but they're mainly problems out of the book. And then the lab documents are out there too with the corresponding Dropboxes. So there won't be any, besides what I have out there for assignment, won't be any assignment besides just, of course, look through it, make sure you understand everything we went over today. So I'll go ahead and stop the video there.